Section 4.6, problem 30, they ask you to solve this inequality. Well, the first step of solving a nonlinear inequality is actually to get 0 on one side of the inequality. So that part has been done for us. The second part is to take the side that is not 0 and consolidate it into something that is altogether in one term and factored as much as possible. So in this particular case, we just need to do a little factoring to make that happen. So I factor the numerator as x minus 4 and x plus 4. Then I factor the denominator, and that factors into x minus 5 and x plus 1. All right, now I can find what are known as my critical points for this expression. Well, the critical points are anything that make the numerator or the denominator equal to 0. And I'm going to put those on a number line, and I'm going to make sure that they happen in numerical order. So the numerator is equal to 0 at positive 4, and it's also equal to 0 at negative 4. The denominator is equal to 0 if x is 5 or if x is negative 1. Now, my spacing might be off on this, but that's not really the important part here. Okay, so now what I want to do is figure out which of these regions includes solutions to this inequality. So every single region is either completely shaded or completely left open, depending on whether or not the solutions for that region will work. So what I'm going to do then is test each region. For example, I can choose any number I would like that is less than negative 4 to see if this region works. For example, I might choose negative 10. Well, we don't have to do all of the math in this particular case. There's actually a shortcut. So let's suppose that we were plugging in negative 10. Well, negative 10 minus 4 is a negative number. I don't even care what the value of the number is. All I need to know is whether it's positive or negative. Negative 10 plus 4 is also negative. So my numerator would be a negative number times another negative number. The denominator, negative 10, is what I'm plugging in. So negative 10 minus 5, that's a negative number as well. And negative 10 plus 1 is a negative number. So I've got a negative times a negative divided by a negative times a negative. Well, there's an even number of negatives. So when there's an even number of negatives in multiplication and division, the result will be a positive number. And since what I'm looking for are things that are greater than or equal to 0, that is exactly what I'm wanting. So I should shade the region that I was just testing, which is this region here on the right. So I've shaded that region. Okay, then test the next region. So choose a number in between negative 4 and negative 1. For example, I'm going to use negative 3. Well, negative 3 minus 4 is a negative number, so that didn't change. Negative 3 plus 4, however, is positive. So that changes to a plus. Negative 3 minus 5 is negative, so that didn't change. And negative 3 plus 1 is also negative. Well, if you multiply and divide, and you've got 3 negatives and 1 positive, the result comes out negative. That's not what we want. So I'm not going to shade this region at all. I'm going to leave that blank. Next, choose a number out of the following region. I'm going to use the number 0 since it's between negative 1 and 4, and it's usually an easy number to work with. So 0 minus 4 is negative. That hasn't changed. 0 plus 4 is positive. That didn't change. 0 minus 5 is negative, that's fine. 0 plus 1, however, is positive. So in this particular case, I have 2 negatives and 2 positives that are multiplied and divided together, so then I know the result will be positive, because those 2 negatives will cancel each other. Since that is positive then, it is greater than or equal to 0, so that is what I want, so I will shade that region. Then the next region. Pick a number between 4 and 5, maybe 4.5. Well, 4.5 minus 4 is a positive number. 4.5 plus 4 is a positive number. 4.5 minus 5 is negative. 4.5 plus 1 is positive. Put it all together, we get a negative result, which is not what we want, so we leave this region blank. Finally, choose some number larger than 5, maybe 100. You could choose 100, it doesn't matter. 100 minus 4 is positive. 100 plus 4 is positive. 100 minus 5 is positive. And 100 plus 1 is positive. Multiplying and dividing with all positives gives you a result that is also positive. So this region contains solutions to our inequality as well. Now, we also need to figure out whether or not we can include the endpoints of these regions as part of our solution. So because there is the or equal to here, we should be able to include at least some of them into our solution. And the reason I say some of them is because we also need to be cautious not to allow the denominator to equal 0. So even if this is an or equal to, I can't let the denominator equal 0. So I'm going to choose intentionally to not include the number 5 and not include the number -1 because of the fact that they would make my denominator 0. Now, if you're familiar with open circles and closed circles on your line graph, this is equivalent to an open circle. Okay, so a parenthesis is equivalent to an open circle. Okay, but I can include the numbers that make my numerator equal to 0. So I can include -4 and +4 as part of my solution. And these brackets are equivalent to a closed circle, if that's what you're familiar with. So if I were to write my solution out in something called interval notation, my solution could go all the way to the left as far as you want. So we call that -infinity. And it kind of stops abruptly at -4, but it does include the number -4. And then I have this interval that is part of my solution that goes from -1 up to +4, where I am including the 4 but not the -1. And then I have this interval from 5 as far out to the right as I want, so we'll call that infinity as well. And then I want to show that there's a connection between all of these intervals, so I use this, what looks like a capital U, but it stands for union, to connect those together. So then that is the solution of this nonlinear inequality.